Okay, so this is class meeting 3. This time we're going to talk about computer vision and Kaggle primarily. So we'll get into, basically you have all of these assignments, and by the next time that we meet in class, they will pretty much all be complete. So all 10 of the class assignments. A couple of, I think around four of you or so are actually done with all of the assignments. One even submitted the Kaggle already. So, but not all are necessarily there. So let's go ahead and go through this. This is just the course information for if people find this online. So assignments 1 to 6 are now complete. Assignment 7 is due tomorrow. I always make the weekly assignment due on Tuesday when we meet. That way, if I don't know, somebody asks a question and I give you some marvelous insight, then you haven't submitted it yet. And the assignments that are due before the next class meeting, which I'll show you just real quick now. Assignment number 7, which is due tomorrow night, is the computer vision network. Computer vision is extremely deep topic, no pun intended, in deep learning, but we don't necessarily have the computing resources or the time to, I mean, you can do an entire semester course just on computer vision. So I mainly just have you go ahead and launch that one. So the computer vision assignment, there's a very, very classic data set called MINST, and we'll see a little bit more about it in a moment. It's digits. And they got these digits from handwritten tests, like ACT tests and SATs. I don't even know what it looks like taking an SAT these days. It's probably all computer based, I'm guessing. But back when I was high school, you would fill in little bubbles on Scantron forms, and you'd write your zip code and your, heck, back then you'd write your social security number on it because they weren't afraid of identity theft in the late 80s, early 90s. So you would fill those all out and you'd handwrite the digits, and that's where a lot of this training set came from. So it's computer image. So I give you some code for this. Basically what you can use down here. This code that I give you basically reads in the data set from MINST load data. So that saves you having to parse it all there. That gets you the training set and the test set. And what I'm asking you to do is basically look at IDs 10, 20, 30, 40, 50, which are actually digits 0, 9, 3, 1, and 6. So you'll notice here, this is what your submission file will look like. My prediction for those was completely accurate. So I'm just basically testing you to see that you can pick out individual digits, submit them to the neural network for a prediction, and get the correct ones. I'll show you a little more on this data set in a few minutes when we get to that slide, but this data set you can predict with tremendous accuracy now. The image recognition has moved on to bigger and much more complicated image sets, but this is a good one to not completely require that you upload something to AWS Cloud or something with big compute. So that's the one that is due tomorrow. Quite a few of you have submitted that one. Then Kaggle. We'll talk about Kaggle because Kaggle is there's 2 projects in this class. Kaggle is the first one. It's a pretty relatively small one. It's what you make of it. If you want to try to get ahead of the other student submissions, you can make it quite complicated and involved. The last assignment, or the last project, which I will give you the parameters for probably in a couple of weeks, and then we'll talk about it when we meet next time, is it's a computer security project. That's a very strong major here at Washington University that I know a number of you are in. So we will basically, what I will give you is a link to a paper, and you're essentially going to complete something based on that. I'm most likely using an intrusion detection system. So you'll get a chance to read an actual academic paper that was published at a conference or a journal. There's a couple of them. I haven't made the final selection yet. I'll probably give you a summary to help you understand it, and then you'll try to reproduce the research of a part of this paper, at least as best as you can. I don't want to make this too complicated, so it won't be a Herculaneum effort, but it'll give you a chance to read an actual academic paper, since this is a graduate level course, and look at trying to understand what the researcher was talking about. I'll give you a fairly readable one. Some of these can be very, very dense. Now, also, that's just one of the options. If you want to choose a project of your own creation for the final project, that is also good. So if there's some data set that you have and you have access to, or some particular thing you would like to apply deep learning to, then that is something that you can spend your last few weeks working on for the final project. The final projects too, I also go through, unlike the class assignments where you get my auto score to basically tell if you've constructed the data right, and I usually only hand grade those if you're not lining up to my data set. The projects, that's the chance where I go through every single one of the little programs that you put together and give you comments as well on that, or if it's your own project. Assignment 8, building a Kaggle submission file. So the way Kaggle works, and I'll show you more about that tonight, but when you submit something to Kaggle, and Kaggle is basically competitive data science, it's how you can compete for actually very serious money. The competitions on there are usually worth a decent amount of money. Some are worth $1 million, some are worth $100,000, and then some are worth like $10,000. So I'll show you a few of those. But one of the ideas of Kaggle is that you do not have to upload your model source code to it. You simply take the data set from them, and they give you a test data set, and you generate the predictions for the test, and you upload that to them. And they know what the answers are. So they will evaluate that and give you back your score. And then your score is ranked with other people who have competed in Kaggle. And Kaggle is brutally competitive, but the Kaggle that we're going to do for a class is just Kaggle in class. So it's really only going to be students from this class who compete in it. Sometimes others from the internet or from the WashU community do jump into. Last semester, a student in the mathematics department who's actually a Kaggle master, so that's somebody who's pretty highly ranked in Kaggle, actually jumped in and competed amongst the students. And so this one, what you do is I give you basically the data set, you download it, you generate your predictions, and you submit your predictions. So you get 2 data sets. Let me zoom this out a little bit. So there's 2 data sets that you're dealing with. This data set you use to train your neural network. So you have your Y in this one. You have the expected outcome. But anyway, download those 2 files. The second one is just like the first one, except that there's no outcomes, just like in Kaggle. So in Kaggle, you have your test data set and you have your evaluation data set. So you have the training data set and you have the test data set. The training one has the outcomes. You use that to train. The submission file, you just send back your predictions. You send back your ID and prediction. I'll show you an example file of that in a moment. So what you're sending back, you just have your ID and target. It's exactly the format you'll use for Kaggle, so that gives you a chance to practice that. Exploring regularization. Module 9 gets into regularization. Regularization is basically a way to combat overfitting. You want to cause your neural network to not memorize things, so you learn about various ways that you can control regularization. And what you do with that is, or control the overfitting, there's several ways that you do that. Mostly you're trying to keep the weights from being too complex. We'll learn about dropout, which is one way of doing that, but for this one, I have you use just L1 and L2 regularization, which you learn about there. Actually, I just have you do L1 regularization. Lasso regularization, as it's called. This seems to be also a popular interview question on some data science positions. We don't usually ask it, but I've seen it frequently on that list. Explain the difference between L1 and L2 regularization. And they're both methods. Essentially, all you're doing is you're adding the weights into the objective function, so you now have two objectives. One objective is keep the weight small, the other objective is get the right answer. So it kind of does an Occam's razor on the weights and keeps them smaller, which doesn't give them the opportunity to overfit. L1 and L2, in a nutshell, if you are ever asked what the difference is between those two, there's several answers, but probably the easiest one is just, L1 is lasso, L2 is ridge. L1 will actually remove certain weights entirely from the neural network, whereas L2 will just attempts to minimize the weights. So you often see L2 used a lot more in neural networks for that reason. For this one, what you're going to do is, the code is almost right there for you in this particular assignment. You're going to do a regression on this. So you're not using a neural network. You're using the L1 regression, which is lasso. And then you basically want to try to generate these coefficients. These coefficients show you the importance of each of these features. So you'll see that it tries to keep them fairly low. So a few of the coefficients basically go to near zero. And that one. All right. So yeah, L1 and L2, I have a whole thing in the class notes about that. Sometimes at first I always want to transpose those, but lasso is L1. Then time series neural network. This is LSTM. And GRU, gated recurrent neural network. So I give you a data file that has some time series information. Now instead of having a lot of X's, so a lot of input columns, you just have one. And you're trying to predict with a sequence size of 5. So if you think of stock prices, this is like 5 stock prices in a row. You're trying to predict the 6th. You do a sequence size of 5. You have to break the data into sequences of 5. I do give you sample Python code to do that. You just need to adapt it to this one. And run it through an LSTM and form your predictions. So this data set, it's a time series. It's basically an ID and then a value that sort of goes up and down. It's essentially... They're points that I made up. It's essentially several knots on a spline. But you teach the neural network essentially to be a spline, is what this one does. The splining and all that is sort of behind the scenes. Okay, so that is it. That is the last of the assignments that you submit. Any questions on any of those? All right. So let me go back to this. So module 6, I'm just going to hit on the highlights. I'm not going to literally go through the videos, cover my presentations on those. I'm just going to give you some of the highlights from these. So backpropagation training, this is essentially where you are taking this is how you get the weights to the neural network. And the weights are the arrows that I have in my very, very simple diagram. But what this is essentially doing is it's optimization. You take the entire neural network and turn it into a function. So the whole neural network becomes just one very big, long function with a whole bunch of coefficients, and the coefficients are the weights. And the function you turn it into is like you see here, where the prediction is output 1. There would be several outputs if this were classification, so this is a regression network. Output 1 minus y. Often squared so that the sign doesn't matter, but essentially that. So you now have this whole thing as one big long function where you're subtracting the difference of what you expect. You want to optimize that big ol' equation so that it returns 0. Because you want the output from the neural network in each case to match the y, which is your expected output. And there's all kinds of mathematical theory behind optimizers where you try to push a equation to 0 or push it to its roots. And backpropagation is just one of those techniques. And this is all based on derivatives, gradients, gradient descent. You take the derivative of the partial derivative of each of the weights, and you use that partial derivative to tell you what you need to do with the weight. So what this diagram that I'm showing you here is basically showing you the error. The error is the y-axis, and the weight value for just one weight is the x-axis. So as you change that weight, the error goes down, the error goes up. You can see there's a nice valley around the weight between 2.0 and 2.5. And this is just one weight. Deep neural networks can have millions of weights. They can be very, 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 very complex. So when you change one weight, you change this plot for every single other weight, at least a little bit. And this shows you what the error function looks like. You can't see this graph though. If you could see this graph, well, you could see it, but it would be very computationally expensive to see this graph. The only way you could see this graph is if you took the weight and you said, okay, I'm going to plot the weight. I'm going to plot the output of the neural network, the error, for every value of that weight from 0 to 3. The problem is there's a lot of values between, there's an infinite number of values between 0 and 3 due to the decimal places in between them. Now this is computing, so technically there is a finite number of values between 0 and 5 in a computer because discrete continuous values really don't exist in computing. There are 64 bits in a floating point, in many floating point numbers, so it might as well be continuous, but technically it's not. So in some of these, so you'd have to decide how many of those values to go through. There's a lot of values. You can't plot every single weight for every possible value that double precision floating point could handle. Even plotting just one weight for that entire range would be difficult. You'd have to plot it for all of them. So since you don't know where that graph is for every single value of that weight, as you're varying just one weight, forget all the others, you can look at what the derivative is of the error function at that particular weight. And the error, the derivative is essentially the slope, which is that blue line. Now you can see that the slope, forget what the slope actually is, that's why it's called the gradient. At this point you mainly care, is it 0, less than 1, or less than 0, greater than 0, or 0. If it's 0, you're kind of stuck because you've hit either a maximum or a minimum. So that is one issue with the gradients. They can get stuck at either maximums or minimums. If you are stuck at the top or the bottom, it's important to know if you're at the top or the bottom. You can actually use the second derivative to tell you that. But the second derivative is extremely difficult to take. You have to use a Hessian matrix, and that gets... most training algorithms don't use second derivatives to do that because it's just very, very computationally expensive, and the matrices that you need to use for those often become... just can't be calculated for the entire training set. It becomes a big data problem really quickly. So you look at just the first derivative, and you can see that, okay, that line is negatively slope. It has a negative slope because it's pointing down like that. A negative slope, that's one thing to remember in backpropagation. You always add to the weight the inverse of the gradient. So you would want to add something to that weight because you have a negatively sloped line. So the most primitive form of backpropagation, you simply add the slope or the derivative to the weight. So say, I don't know, that slope was around negative. I'm horrible at estimating. The only thing that I'm worse at estimating graphs is actually drawing them. But if that was negative 0.5, which makes it easy, you would add a 0.5 to it. Usually that would move you too far. So you usually multiply some percentage by the slope. You don't want to add the entire slope to it. You just add a percentage of that, and that percentage is called the learning rate. So the smaller you make the learning rate, the more gradually your weights are going to be changed. So anyway, this is one interesting fact of deep neural network training. Despite all the very advanced features in deep learning, it's still at its core gradient descent and backpropagation. There's just all kinds of mathematical tricks that deal with all of the problems that you run into with gradient descent. One of the biggest is if that line is fairly, that diagram that I have there, the black line, that's a pretty convex search space. That's a pretty convex error form. If it looks more like a earthquake seismology report, then it's very, very difficult to optimize because there'll just be all kinds of little valleys that you can get caught in. And there are ways to handle that, but if the error function looked nearly random, just all over the place, it's almost impossible to truly optimize. So you'll look at these for optimization. Let me show you just a couple of the notes that I had on that. This is kind of the basis of... So this formula here, theta, is typically, in neural network notation, theta is usually the weight. So theta t just means, and this is a little tutorial on how to read papers on neural networks. They use a lot of the same symbology. T usually means the current training iteration, the current training step. So theta t means the weights at the current training iteration. And that first equation, all that's saying is for classic backpropagation, or really for any training, you set the value for the current iteration equal to the weights from the previous iteration minus the weight change amount. The weight change amount is essentially going to be the inverse, so that's the slope. And VT, you calculate that essentially by the learning rate, eta. This little harp, that's not a delta, if you've never seen it before. It's an upside down delta. It's the nabla. It's a harp-shaped thing. And that essentially means we're taking the gradient so the derivative of the weights at t minus 1. So the weights from the previous training iteration, that's the percent that I told you. So we're multiplying the gradient or the weights at the previous one times that learning rate. If you made the learning rate 1.0, it would move too fast. You'd be coming down the valley and you'd probably jump right over and you'd be on the other type of the valley and you'd just be bouncing back and forth and you'd never really converge to anything. And then J is the error function. That's what the nabla is operating on at the weights minus 1. So we're taking the partial derivative of one of the weights and of each of the weights, a vector of them. Common learning rates are usually things like 0.1, 0.01, and so on. If you never want a learning rate. I've never seen a case where a learning rate greater than 1 did really anything. Otherwise, your weights would be bouncing all over the place and failing to converge. You'll also hear momentum backpropagation. What is cool about that is you add a momentum term, so lambda, and all you're doing there is you're taking the v, so the change in weight from the previous iteration, and you're also scaling it. You're usually more aggressive with a lambda. It's usually about 0.9. And all you're doing is taking the change that you previously had and scaling it and adding it to it. So if you were rolling down a hill like this, the momentum hopefully would give you enough energy that it wouldn't decay to the point that you wouldn't be able to hop over that intermediate hill there and pass that local optima and hopefully continue to that local optima. You never know that you found the global optima, so the best place ever, because this goes for infinity. Weights could be negative 1,000 if need be. The neural network can train it to that level, or they could be positive 1,000. There's a whole lot of values. The rest of this I will let you hear me describe in the video. The only thing that I do want to mention is there are some very advanced training techniques now that are available for deep learning. One that I've had pretty good luck with is ADAM. It is adaptive estimate of moment, and it was introduced in 2014. So there's been a number of other improvements even beyond this one. But one thing that is good about ADAM and ADAGRAD and some of the other recent innovations is you end up with a learning rate for every single weight, because not all weights learn the same. If you're trying to push every single weight at the same rate, you'll very quickly, you'll never ease into a really good final value, because not every weight learns at the same speed. And those are just the equations for ADAM, and I take you through those in the class notes, or the class video. If you want to see backpropagation completely in action, see how every calculation is done, and I've had classes where I've had to do that, where, if you take some of the machine learning courses, especially the theoretical ones, you won't use TensorFlow, you'll write TensorFlow. You'll write your own neural network gradient descent program from scratch. It's not that hard. This is essentially just power rule and chain rule of derivatives, just all the way back to, you take sort of the innermost one, so that's why it's called backpropagation, because you're starting with the innermost function, which is the output, and calculating back. This is a program that I wrote in JavaScript, which is actually based on I think, a C program that I wrote when I was undergrad, working on one of these. And it basically, calculating it is not that hard. You would take whatever the input is, 0, you would multiply it by that weight and by that weight, you would sum, and you would do that for every single one of these, and then you would sum all of these input arrows, put the value there for hidden 1. You would sum these 3, so the input 1, the input 2, and the bias. The bias is always 1 because it's just an intercept, and you'd put the value there. So to calculate this whole thing, you would calculate hidden 1, hidden 2, then you would multiply hidden 1 and hidden 2. You'd apply the activation function or the transfer function once you'd summed them and put that into there, and then you'd multiply each by these weights and put the final sum here. And if you click Calculate for Input, it does that entire calculation for you. It's written in JavaScript, so it runs on the fly in the browser. And if you go down here to the very bottom, it spits out the actual calculations for this. And you basically have the entire output of the neural network there. So you can see the sums getting calculated, sum 1 and sum 2 and sum 3. That would be sum 1, sum 2, sum 3. Now if you want to train it, notice how long that equation is. If you want to train it, you basically then can use this. And I give you a learning rate and I give you the momentum. One thing about training though is it can be done batch or it can be done online. This is a very simple neural network that is learning to be the exclusive OR function. So exclusive OR, basically if the two inputs agree, 0 and 1, or 0 and 0, it's going to be 0. 1 and 1, they agree, it'll be 0. If they disagree, it's going to be 1. So that's the exclusive OR operator. It's a logic operator along the same lines of AND, OR, NOR, all of those. When I took probably my first machine learning class, what my professor just loved to do was you would have a diagram, you would produce a diagram like this, but he would give you a complicated logic expression like X or X2 and something else, not the whole thing. He'd give you this, just like if you've ever taken first order predicate calculus. You have all these ands, ors, and nots, and fun things like that. You can express that all as a neural network, and you don't need backpropagation to tell you what the weights are. You can just hand code the whole thing. It's kind of tedious, but you really learn how a neural network works. But to train it, first you do the whole calculation for the first element, and then you can update the weights. Or you can sum up all the derivatives, all the gradients, and then calculate the weights. So if you do just one of these, train online, you will see the weights adjust just a little bit. If you want to train in batch and do all 4, you click that. And I don't quite have enough room on the scrolling, but if you click that, you'll see that basically the weights are changing, and the mean square error is very, very slowly going down. We probably might be able to get more aggressive on the training rate. Well, it's in a little bit of a local minima there, so I'm going to leave that one alone. But if you play with it enough, you can get that to converge down, and then the weights become at least fairly optimal for that. You can see all the calculations that go into a single sort of iteration of backpropagation. And I used these. When you're implementing something like this, it can be very useful to see all the intermediate calculations just to check and see if your equations are correct. So I've gotten, I don't know how many questions on this particular page from students who are implementing their own backpropagation and asking me various questions about it. And one question that I do get, that I was getting a lot, so I added this whole part here, for the sigmoid function, which is what this is using as a transfer function, I use a more optimal, I describe basically the whole process here, how you get so this is more in mathematical notation, this is more in computer programmer notation. All right. So if you want to see it down to the nitty-gritty theoretical, that will show you. Convolution neural networks, like I said, you can do an entire course on this one. I'll show you some of the basics on that. The class lecture goes into more detail, and I'll show you a link to a class at Stanford that is completely online Well, you wouldn't get any credit for it, but you can follow the online lectures and learn all about. Okay, so convolution neural network structure. First of all, just the data sets. These are a few of the more introductory data sets here. You have the MENS data set. The MENS data set has pretty much become the hello world of convolution neural networks. The CFAR data set, which you have here at the bottom, airplane, automobile, bird. This was generated originally from Google, but these are very small images. You can see the automobile, that whole row, those are all automobiles. The bird row are all birds, cats, and so on. For a convolution neural network, we have several different layer types. That's the big change. Up till now, we've mainly had dense layers and input and output layers. And we still have dense layers, but now we have convolution layers and max pooling layers. Later on, next class, we'll see dropout layers, which is a form of regularization. But these are the workhorses of computer vision. And then there's ResNets and other things that are just this, but extremely, extremely deep. This is your classic convolution neural network structure taken from Jan LeCun's original paper on the topic. The real advance here in convolution neural networks is this convolution layer, which you see on the far left, you have the input. He's using a relatively small input space of 32 by 32. Usually you send three-dimensional data into a CNN, so that's 32 by 32. That would be absolute monochrome, black and white. You will sometimes see, or very often you'll see 32 by 32 by 3, and you'll have a depth then, and that 3 depth is RGB, or some other color encoding. But what's very powerful about convolution neural networks is you have the convolutions, which is that little rectangle that you see on the A, and that scans across it. So it's constantly scanning, much like our eyes do to take in the whole picture. And it lets the neural network be able to learn, so just the weights between that first layer and the convolutions, so there's 6 convolutions in that second one, it lets them scan across, and the weights are shared as it scans. So it's not learning all that much when it's scanning across in the upper left because there's no pixels there, but as it scans across, it starts to learn edges and other features of the letter. So it might learn, okay, here's a common thing where the bar of the A and the arch part of the A come together. Maybe you've got the top of the arch. And those feature maps in the second layer start to learn those individual pieces of an image. And by the time you get all the way out to the dense layers, Jan LeCun calls them full connection, but it's basically a dense layer. And then the Gaussian connectors that he's got on the far right, that's essentially doing the same as the softmax function. So that's dealing with classification. A lot of these images, they classify, they have it'll be bird, dog, cat, automobile, airplane. So all those classes that it's going into, those are what he's using those Gaussian connectors to give the actual final probability. His output is 10 because there's 10 digits. By the way, that is one thing that is something of a limitation on a lot of these algorithms. They classify into known classes. So if it's trained on the 10 digits and you give it the letter B, it's probably going to tell you that it's an 8 because it's never seen the letter B. And that's not, so if you want to have the neural network give you an I don't know answer, that can be a difficult thing for some of these convolution neural networks. What they're now doing, though, is combining the LSTMs and the convolution neural networks, and they're teaching them to actually auto-caption. So you can actually have the neural network look at an image, and it'll tell you something like, this is a person sitting at a table with an apple in front of them, or something such as that. So that's a very powerful feature, but that's using that's using the convolution neural network to generate the features, and then a LSTM to generate the output and automatically caption it. So it's NLP meets image recognition. And the convolution layer, the whole idea is it does the scan, so that blue region or cyan region is essentially the scan as it goes across. Usually you pad the whole image in zeros so that it has a consistent starting point. A 1 pixel pad is pretty common. Oh, and max pooling, I didn't mention that, but that's another, I mentioned it in the videos. This is essentially decreasing resolution. So if we go back to this first one, he does the feature maps with taking the input and reducing it down to that 14 by 14. The subsampling is what takes it down to the 14 by 14. So he basically cuts his resolution in half and it pixelates it. It's just like if you have an image. So if you take a real low-res image on your cell phone and you blow it out, it's sort of pixelized. He's dropping the resolution as he goes, because as he gets more and more feature maps, all those details are less important. And I don't do a whole lot on image recognition. It's definitely not an area that is one of my research areas, but the max pooling layers are a bit of a controversial area. There's, I think, Geoffrey Hinton in Reddit, believe it or not, Geoffrey Hinton participates on Reddit in a Ask Me Anything sort of session, said that max pooling might have been one of the most misguided steps in machine learning or in computer vision. They seem to have stayed around, so I don't know. There's competing ideas on each side. They are throwing away detail, and as computers get stronger and stronger, maybe that's less important to do the downsample. So of these data sets, I showed you the minced. I will show you the kind of the homepage for minced, because it is kind of interesting. This is sort of the origin of computer vision. Jan LeCun has had this page up forever. He describes basically the format of this. Usually when you get computer vision files, they don't just give you a ton of JPEGs, because that would be very large. Usually they're compressed and represented in some sort of proprietary way that the author then goes on and describes here. But this is the part that I find pretty interesting, this table right here. This is updated a lot over the course of computer vision research. So if you go back to the very beginning, this is almost like a little, not even a little, but an early Kaggle competition by Jan LeCun. You see here, he pre-divides the data. So he gives you the training data and he gives you the test. So he specifies how you break it. And that's a very important thing to do. That's why Kaggle has a defined test set. And that way, the results are reproducible. Like when we work on a data science project, we almost always break it into 10 folds ahead of time, and that way every data scientist is using the same folds, and that lets us be able to combine our models together at the end. So he pre-breaks that, so you don't have to worry about somebody, because otherwise, if you didn't pre-break it, somebody could publish a paper and they could be very sneaky about it. They would try a bunch of different different partitions, and they would find the right seed that gives their algorithm the advantage, and then you would publish that. But since he specified it on his test set, this early one, this linear classifier, and he has links to the paper, so LeCun, that's him, published in 1998, was getting a 12% error rate. He tried a different approach. Deskewing, these are just pre-processing things that he did on the image before it goes in. That's the idea with deep learning. You don't have to do all the image pre-processing. It learns how to pre-process the image. And you can see that this error rate gradually decreases over time. So by 2007, the error percent is below 1, and the one where it shot up there, that's LeCun's, he's basically just demonstrating a new type, basically showing that you can really subsample this with advanced techniques and still get a decent error. And then finally, so yeah, so most of these are under a percent. All these various different ways. And this used to be a way that I don't think there's really that much active research on this data set because it's kind of been beat to death. But every time somebody gets that percent to a little bit lower, you're pretty much guaranteed a paper. Unless you absolutely have no idea how to structure a academic paper, then they'd probably still reject it. But there are a few cases where a paper has introduced a new and very important innovation, but it's just not structured properly that it can be published. So often you find an ally who has more experience than you in publication, and you get the idea published. Just win a Kaggle competition with your new algorithm, and you'll have no shortage of luminaries wanting to co-write the paper with you. Okay, so that's the origin, sort of things. I do want to show you, for computer vision, if you do want to go deep in this, there is a researcher, his name, I hope I can pronounce at least halfway correctly, but Andrei Karpathy. He was a PhD student at Stanford. He has since graduated and now works for Tesla, I believe. And he taught a class, a very famous class at Stanford on computer vision, and all of it is online. If you want to go deep on computer vision, this is a very good, and Stanford has since taken up the challenge of his class, and look, I mean, that's how many people and teaching assistants they have going on this particular class. So you can, all of the lecture material is completely online. They even give you the information for the assignments and the big final project that they have you do, and all the videos are recorded. So it's, if you want to go deeper on that, that is definitely, by the way, his thesis, which he defended, I think in 2017, was on auto-captioning. So basically you have a cat, and he was able to use natural language, not necessarily processing, but rendering using an LSTM. He gives you the whole architecture there, and is able to caption that, saying a cat riding a skateboard. So this is kind of the new frontier in image processing, is you're learning to, you're not just looking at one picture and saying what it is, you're finding components of those pictures. And he describes an ImageNet is the big data set for that. It takes a lot of compute power to, yeah, I really like this. This is probably the main reason that machine learning researchers are interested in JavaScript, but you can create really cool, kind of like I did with the backpropagation calculation. This is something that Andre created for the convolution neural networks, and you can see basically the scanning happening there. So it's like the diagram that I showed you on my page, except his is completely animated, and you can see how the weights are calculated for each of these. So that's the convolution layer, and each of the convolution neurons, you can see that the weights are shared. So weights for something calculated way up in the upper left hand could be found in the lower. So if you move the image around, it should still be able to recognize it. And you can rotate things even. There's a very good video where he demonstrates essentially a 9, and it's saying 9, 100% probability, and he starts to rotate it. Eventually he rotates it completely upside down, and by the time it's upside down, it's saying 6, 100% probability. But the probability literally clocks and adjusts as he rotates it. So if you have a 9 laying on its side, who even knows? It's a 9 or it's a 6. You can't tell. You don't know what way it was knocked over. And I'll show you one other. ConvNet.js is something that he wrote and used for his classes. He's not really maintaining it all that much anymore, but he implemented convolution neural networks in JavaScript. So this is actually training and learning completely in your web browser. And it is training a neural network literally from scratch. And you can see the loss function, the error function being plotted over there eventually. So this is running entirely on my computer. And you can see the images coming into here. So boat, I guess that's an airplane. And you can see what it's learning on the convolution layers. The convolution layers are essentially learning edges, at least at that point. And then even higher level of abstractions. Then it pools and loses the resolution. So you can literally peer into its mind and get an idea of what it's doing. And then you can see it running here. So as it's learning, okay, ship, if it's green, it's getting it right. So ship has the highest probability. That bird it thought was a cat, but it's just started. So if you let this run for a while, this is a really good page to go to just for a quick demonstration of image recognition technology, and all running in JavaScript. It's truly amazing the things that they have converted into JavaScript. Okay, we're getting to Kaggle. Let me just give the introduction to Kaggle, then we'll take the break. Let me go ahead and pass around the attendance sheet before I forget. Whoever that lands with, just go ahead and drop it back on my desk, probably somebody in the back row. So Kaggle is basically data science competitions going on. There's always been data science and machine learning competitions. The Netflix prize, you might remember, that was $1 million. Just all these sort of competitions. Some of them have no money, some are just for bragging rights. These are a few that I just took a screenshot just to show what Kaggle looks like, but you can see there's decent money being thrown at these. One of the reasons that people compete in Kaggle, I know a number of people who have done quite well in Kaggle and never actually won any money out of it. As a data scientist, it gives you sort of a bragging right. It doesn't count in absence of experience, but if you've done this for a while, it can definitely. I know at a competition somebody saying, "Oh, I'm a Kaggle master or grandmaster," is basically, it can be somewhat difficult to get to. But the levels are novice. That means you've signed up. You haven't really done anything. Contributor, you've competed in one competition. Expert, you've done a couple of competitions and you've actually won 2 bronze medals. That means you're in the top 10% of 2 competitions. I've done a little bit with Kaggle. I've done about 3 competitions, and by the way, I am expert level. So my level I can consistently place in about the top 7% of a Kaggle competition. Master would be the next level if I want to get into some more of these, and I probably will try more Kaggle competitions as I have time. That would mean you've won 2 silver and a gold medal. So to do that, I would have to place in the top 5% twice, silver, and I would have to get a gold medal. That would mean I would have to be in the top numeric 10 of the people who were. That would be the hard part. And then Grandmaster is, I know a number of masters, and I know one Grandmaster that I sometimes speak with at conferences. But these are all of the levels for that. So if you get a Kaggle page, that's basically what it looks like. So that would be me. I have my 2 bronze medals and none of the higher ones. So of the 78,000 people in Kaggle, I'm at 3208. So it's just sort of a way. What I like about Kaggle is I can learn. There's message forums on these, so when I compete in a Kaggle competition, so like the Quora question pairs, which I got to 225th on that one, I'm reading from the people who are higher than me and posting their solutions. It's one thing to look at the answer. So if you look at a solution to a problem, if you've never tried it, it's one thing to look at a solution, but it's another thing to have beat your head against the wall for a month trying to figure out something and then seeing the solution to somebody who has done it quite a bit better than you. So that's what I like about it. I get to learn from the best, so to speak, because I beat myself up on it for like a good month trying to learn it, and then I can read the... All right, I will, when we come back, I will show you the project, which is due after the assignments are all complete. You can make the Kaggle as complicated or really as simple as you want, but we'll take a 10-minute break. Let's see what time it is. It's 7:13 now, so we'll start up at about 7:23. All right, we will go ahead and continue. So let me show you the Kaggle competition that we did last semester. So last semester, this one turned out pretty good. Not all of these turn out quite as well as other ones. The data typically comes from a market simulator program that we use actually to model various things, and I just usually run it to generate test data for the Kaggle. So it's simulating market conditions and prices and other various things going on, and it's a very complicated model, and it's somewhat random. They call it a stochastic run. And I see how well you can use the neural network to predict the simulated... So it's like predicting, I don't know if any of you have played SimCity, but SimCity is sort of a example of this sort of a model. So any Kaggle competition that you go to, and I'll show you just a few features on last semester. These last semesters, it's not necessarily that important to you. So if you... I'll show you on the profile, that's me. So if you look at the leaderboard on this one, those are all of the people who competed. And what's interesting when you look at this is the little dots, they call them pips, the little dots underneath the individual's pictures. So if you went to a competition that I had competed in, you'd see 3 dots and they'd be purple, indicating Kaggle expert. The people with 1 dot are all the students who, most of the students anyway, who had this was their first Kaggle competition ever. Alexandru Papu is here. I don't know if he's here anymore. At that semester he was in the mathematics department. You notice his pips. He has 4. He's a Kaggle master. So he's done quite well in this. And he dropped in and competed. I don't think he tried particularly hard because he only had 2 submissions. But he had heard about it through other... And I do get requests from other... I think, because you know how you use your API key to submit your assignments. I've had a few emails from other... people in other departments, hey, can I have an API key so I can at least see if my solution is correct? And usually, yeah, they're here at WashU. I don't care. I will give them one. But you can click on them and then see their page. Okay, I don't think he's here any longer. I believe he was a doctoral student at the time, working for Simula Media. And he's got his link, and it's a recruiting thing, absolutely, because he's got his LinkedIn page and his Kaggle or his Twitter and other things there. The person, and you can see too, it tracks what your score is. So in this case, lowest score wins. It shows the last time you submitted, which was 4 months ago, which was last semester. The number of entries that this person did. Louis Winthorpe, the third. Some of you might recognize that name from the movie. I think it was in the 80s. Trading Places, I think. So he, that was the student's alias. And this was his first time in Kaggle, and then he basically got that score. This student who now has 2 pips, I know him, Luis. Luis is actually coming to join us at RGA for a summer internship. So he did really well. He is a doctoral student here at, I think he's a candidate at WashU. But you can tell the ones that really got into it. He submitted 22 times. This student was pretty advanced in new machine learning techniques, even beyond deep learning, and he used an ensemble to totally get to that level. But anyway, you can tell by the pips what level people are at. And this page updates. So if some of these students get interested in Kaggle and become an expert, or this guy, I don't know if he was one of the students, I don't remember, but he has competed. You'll notice too, it says team members, and you'll see we really didn't have any big teams. Kaggle allows you to combine into teams. So for this assignment, I will allow you to combine into teams. If you want to do this as a group, that's perfectly fine. Just don't amass into one big group. That's not allowed. I would say no more than 5 at the most. I didn't put in a limit there, so if you want to band together, that is perfectly fine. Or you can be lone wolves as well. And by the way, to get the grand prize, the Kaggle Grand Master, one of your gold medals has to be alone. So go Kaggle. Well, Kaggle's owned by Google now, but does make you do at least one solo. So I won't do any of the team dictations. I don't know. I used to hate graduate classes where they'd be like, okay, 1, 2, 3, you're a team. 1, 2, you're a team. So, although usually you sit by people that you know or don't inherently dislike, but who knows? You might be masochistic. So feel free to join those up. As far as the top score, you don't win really anything in particular. The top 3 or so, if you're in the top 3 or 4 and you want to write your final project on what you did with your Kaggle, you can do that. That's about the only thing you sort of win. The other thing that is good, occasionally I get requests for letters of recommendation, and the better a letter of recommendation I can write, the better I know things interesting to say about you. So I have had people, because I've done this for probably 4 semesters now, I have written a couple of letters of rec I can say, well, they won the top position in my in-class Kaggle competition using X, Y, and Z, whatever you happen to make use of in that. So other than that, just bragging rights, the page there remains even after the class. So you don't have to use your real name unless you want to. Some do. Luis Garcia did. Okay, so that's the leaderboard. And that's for the one in the past. By the way, I don't enter into the student competitions for several reasons, one of which I have the answers. So I could completely cheat if I wanted to. And 2, just in case I happen to jump to position 1, I don't want to, when I talk about a student, say, well, they were in position 2, but it really was 1 because, so I don't enter into that. I usually do write a solution for it fairly quickly just to see where I can land. I think in this one, my sort of 3-hour solution was right at 4.5, right between these two. I know he put quite a bit of time into that. He was having a lot of fun with that. So let me close that. This is the one for this semester. So it's pricing office supplies. And that is no more than a picture of one corner of my desk. So it's just what I had it simulate. Feature engineering will help you on this one, most likely. Let me grab the data. So every Kaggle competition has a data tab, and if you go to the data tab, there are 3 files at a minimum. Sample is a sample submission. So I'll go ahead and I'm going to download all 3. Test, that's what you're evaluated on. And the train, that's what you build your model on. So you usually have these 3 files. Test and train are the 2 most important. That shows you, train is what you're going to train it on. Test is what you're going to actually test it on. Okay, so good old Microsoft Excel. Probably the most convenient, yet worse CSV file viewer ever. Thing you have to be really careful with Excel is it strips off leading zeros. I wish Excel just had a don't do anything stupid with the file mode. That would be really cool. This is why you want to be careful with Excel. An alarming number of scientific papers contain Excel errors, some of which have gone to human medical trial. So be careful with Excel. And the way it does exponents does not completely match with traditional mathematics. So be careful with that as well. So the train file, this is the training file. It gives you the IDs. The IDs are most likely not valuable. All Kaggles have IDs. The IDs are not supposed to be important. But in Kaggle tradition, there's something called a target leak. And a target leak, there's a number of things that you do in Kaggle that you would never do in the real world. In the real world, a target leak will kill you. In Kaggle, it'll really help you. A target leak, so you're trying to predict the cost. Say I had my data sorted by cost, and the ID incremented along with it. So the low costs were here, the high costs were at the end. You always want to randomize your order. But if you sign the IDs so that low costs would have an ID closer to 0, there would be a correlation between your ID and your cost. So a target leak is when one of your data items has information that you would not have in the real world. So these IDs will sometimes become important in Kaggle competition. It means that the company that submitted the data set did a bad job randomizing and selecting their data. Target leaks can be profound in Kaggle. Sometimes they will have to rerun a competition just literally because the target leak was really bad. And sometimes people find it by mistake. There was a Kaggle competition called Santa's Helpers, where you're trying to find the optimal route for Santa's sleigh to deliver all the presents. You know, the whole thing of, does anybody still believe in, no, I'm kidding. But, spoiler alert. So, how to find the optimal, I mean, obviously Santa is going around on that sleigh at the speed of light, dropping to hit truly every point that he needs to. So the problem, there was a leak in that one, and somebody happened upon it by mistake. It was basically probabilities, so you're supposed to, I can't remember the exact thing, but somehow in the data set that you were submitting, you weren't supposed to put negative numbers into your probabilities. But one person accidentally did, and those negative numbers, it just so turns out, they didn't have a check for that in their scoring algorithm, and it gave him a phenomenally good score. And he was immediately at position 1. And when you pop into position 1 or 2, been in position 1 or 2, I've never maintained it till the end, you start getting lots of pings from people literally writing to you, what are you doing? How did you get to there? Anything you want to share? And that person who was there said, I don't know. I've only started learning data science about a week. I thought it would be fun to be in a Kaggle competition. But yet he was number 1 by a huge margin. It was like, to use the saying, you brought a gun to a knife fight, that was him. I mean, everybody was just way below him. But then he Kaggle announced what his score had done. So he went from being this highly revered genius to oh, okay, you had a programming bug. That's why you were number one. But I think they gave him some sort of consolation prize for finding the bug in their algorithm, completely by mistake. But target leak, you don't want that. I'll give you an example of a target leak in our own system. We had a data set where we're trying to predict claims fraud. So did you commit fraud on a claim? We have humans who are trying to predict if you committed fraud on a claim or not. One of our columns in our database is something called settlement amount. So if you submit an insurance claim and we settle it with you, that means that basically we paid you the claim. You're done. That person used settlement amount as one of the predictors. You don't know settlement amount until after the claim is processed. And if we paid it, that's probably a pretty good indicator that the human claim adjusters have determined it's non-fraudulent. So he used a value that you would only know in the future. That's a target leak. And Kaggle target leaks happen because the problem with competitions like Kaggle, they're giving you data where they know the outcome. And usually they know the outcome because they're looking back into the past. If you look into the future, you won't have it. You need to really be sure you think of what you have in the future. A question I was answering in class in between that was a very good question is, if Kaggle knows the answer already, what are they trying to accomplish? Well, if you look at one of the $1 million Kaggles, which was Zillow, can you predict the value of a house? They gave you a bunch of data where they were looking into the past. Houses had already sold. So what's a house ultimately worth? It's worth what somebody will pay you for it. So that's why sometimes when when you own a house, you get this letter from the tax office and they tell you what they've assessed your house's value to be at, and that's what you're going to be taxed at. And half the time when I see, really, my house is, I would sell it to you right now, Mr. Taxman, if it was worth that. But so usually they inflate it a little bit since it's taxes. But what Zillow does is you train it on this, and then to get the $1 million, now they're going to stop it, and they're going to give you a bunch of houses that haven't sold yet. And you predict the price on those houses that have not sold yet, and then 6 months later, when a number of them have sold, then they know how accurate you were. So that's why it takes 6 months to run it took 6 months, it's over now, to run the $1 million Zillow Kaggle competition. So target leak, I really tried to not have any target leak, but if the IDs are predictive, that means that the orderer here means something. I randomized the heck out of it, so you can try the IDs if you want. They might help. You're trying to predict the cost. So here's the information about these items, and you're trying to predict what the cost is, and the cost is market driven. So I ran this simulator over, I think, a couple of years, and that's what the prices on these various items converge to. You're not going to run it in a stochastic simulator. You want to use a neural network to predict it. So some of these values, like name, well, the auto miles per gallon data set, you usually strip off the name of the car. The name here is important. There's data that you can extract out of this. Large red generic paper clips by Whizbang. That is the name of that product. And the manufacturer here is Whizbang. Some of the manufacturers put their name into the products, some do not, like high quality pink small pencils by the manufacturer is 6% solution. You could probably do dummy variables on the manufacturer because there's not that many of them. So it would go good as a categorical. But there's information about these items that you can definitely extract if you want to do string parsing on it. If you want to do just the very basic model, just use your numerics and see how well you can predict the cost. If you want to go more advanced, find colors. Colors might mean something to the actual cost. Pack is the count. So how many pencils are there in a pack? Maybe larger packs give you a smaller unit cost. That might give you some information there. Maybe the weight has something, weight divided by, so the individual weight of the item, so the pack divided by the weight, that would be the individual. So you could extract that feature out of it. Height times width, length, and cost. So feature engineering is one of the key things for Kaggle. And that's one thing I was discussing with a student at the break, is how do you get to, so to get any of the metals in Kaggle is non-trivial. If you just throw together a solution using just basic data science knowledge, you know how to make dummy variables, you know how to cross-validate, you do all of that, you'll usually break out at about 25%. To get higher, it's, or at least in my case, it's feature engineering. So the one where I got into 7%, I engineered the heck out of those sentences. I would take my data and look at the ones where I was the most wrong, and look at those one by one and see as a human being looking at those, okay, what is wrong with those? Why is my model confusing those two at the top, and then, I'm sorry, those two. In that 7%, it was the Kaggle Quora competition, the one that I've done the best on. They would give you 2 sentences. And the 2 sentences, you had to say if they were the same sentence or different sentence. And some of them were tricky, like one that my model was initially confusing is, what is it? What is lowercase it versus what is capital IT? So what is it versus what is IT? IT is information technology. It's a type of department. So capitalization and acronyms, I ended up creating a lot of features on that. The data, and this is not at all a political statement, but the data came from Quora, so where people were asking questions, right smack in the middle of the 2017 US presidential election. So there were tons of Trump questions and Hillary questions. And I had to literally create a Trump model and a Hillary model. And one thing that I found very interesting is in the questions how those 2 candidates were referred to. Trump was always referred to by his last name. If you wanted to refer to Trump in a question, is Trump running for president? That's how you would say it. Hillary, you would always refer to her by her first name. You wouldn't call her Clinton so often. Some people did, but probably because her husband is sort of the Clinton. So I had to engineer all kinds of stuff around that. It was, let's see, was the election still going on? Not that would have helped in any way, but I think the election was, no, I think it was over at that point. I can't remember.
Because there was no one was able to predict the results. All the rest were...
Okay.
Which I thought was odd because I was trying to predict it also through the...
Yeah. But, and Nate Silver did a great job on that, the one before. But yeah, it's... And also the 2017 election, too, was where psychology trumped data science for sure. But it was a lot of interesting things in that one in terms of sampling error. So anyway, that's the data set. So your target is the cost. Let me show you the test data set. So this is the test data set. Notice the IDs are larger because none of the training set is in the test. And you notice we have ID, name, manufacturer, all of these, length, but we do not have cost. You need to fill that column in, and that becomes your prediction. And all you return is just ID and your prediction, cost. You don't need to give me these values back. I already know what they are. So don't echo those back to me. I think Kaggle actually gives you an error if you do that. And the sample is a sample. That's what you'll send. You just send me your prediction. And most Kaggle competitions will include a sample file. So I don't know, say I had to write a model to predict the average GPA for a student at Washington University. What would be a very good, just baseline, really stupid model would be if I just took the average GPA of all of the students. And that's what I did here. I took the training data set and I calculated the average cost, which is 130, which will be, it's a total dartboard calculation. And if you submit this, it gets a certain error. You could submit this one if you want to. That's a decent opening bid sort of for it, just to see if your data, just to see if you know how to use the Kaggle interface. So those are your 3 files. You'll submit something like this. If your rows are different than this or your IDs don't match up, Kaggle will give you an error. There is a discussion area. If you want to, you can post a discussion topic. Piazza is also good. I won't monitor the discussion area actually on the Kaggle necessarily. The students haven't really used it in the past. And the rules and all of these are just format my HTML for some reason. I might have to edit that. Team. You start out on a single team with you as the leader. Teams can merge, you can do all kinds of things. If you're competing in Kaggle at the highest levels, there's very interesting things for how you combine teams, because the teams don't necessarily trust each other. They want to know if they're 2 models. In Kaggle, a big thing is ensembling models together, and there's a pretty straightforward mathematical way of combining 2 models where whatever the 2 were individually, the combined model will not be weaker than the 2 inputs. It might not be much better, but there's ways that they can analyze the statistics and know if combining, without disclosing too much information to your potential. Because you don't want to send your data set to another team and then they just say, yeah, thanks for that. That boosts us by this amount. Nah, we don't want to do a team. So there's ways to handle that and to evaluate if they would give you much lift by ensembling together. So anyway, that is the Kaggle competition. All you have to do is make a submission, and then in Blackboard. So we haven't used Blackboard submissions for any of the 10 assignments. You just submitted them with your API key. For the 2 projects, you will use Blackboard. So what you'll submit to me in Blackboard, you can submit your code if you want. I don't actually need your code. I just need to see you in the leaderboard. Submit to me a text file that basically says that's either the URL of your profile or your Kaggle name. So for me, I would just submit that URL. www.kaggle.com/Jeff Heaton. And again, you don't have to use your real name. But I need to know who you are so that I can give you a grade. And if you're on a team, just tell me your other team. Every teammate needs to submit it. But if you're a team of 3, all 3 of you should submit the same 3 URLs as your team. You don't get anything, you don't get like, I have seen professors do Kaggle. I think that's actually kind of mean. They do Kaggle competitively. So, okay, the top 80% are going to get an A, the lower 20% are going to get a B. So basically it's impossible for everybody to get an A. I've had professors do that. I don't like competitive grading necessarily, but it's a way of doing it, but I'm not doing that. So this is mainly a test of, can you get the Kaggle data into there, and can you should get something better than submitting the sample. If you submit the sample, I forget the score for that. I'll know you just submitted the sample because you'll have a very low score. But that is the Kaggle assignment. And then I'll give you more information on the security assignment. It'll be somewhat similar, but it'll be write a program sort of reproducing some of the research on a paper. I will probably give you an option too on the final one, just in case you're completely sick of programming by this point, to write an analysis on the paper, on the the academic paper. So I'll give you a couple of options there, or you find your own data set and do your own model on something that interests you. So those are your 3 options for the final project, and then that's the entire class. Any questions about the Kaggle? And I do have a video explaining it as well.
Due date in the syllabus?
Due date. Very good question. So Kaggle has a due date. All Kaggles have a cutoff. And the cutoff, thank you for asking that, because you have to be very careful of the Kaggle cutoff, because the Kaggle cutoff is not midnight. It is midnight in Greenwich, England. Universal time. So, which is around 6 o'clock our time, I think. It depends on daylight savings time. But if you go to the overview, here's the timeline. So I launched it actually 9 days ago. The end is here, April 10th, 2018. April 10th, 2018, at Greenwich Mean Time midnight is when this closes. And Kaggle is quite brutal on that. It will not let you, if you haven't submitted anything until then and you wait until a day after, it will not let you onto the leaderboard, which is how you get your grade. So make sure that you get that submitted and that you get the Blackboard submission as well. Failing even Blackboard, you could email me and say, hey, here's where I was on the leaderboard. If you make your leaderboard name your student name, then I'll definitely figure out who you were. But you're not required to put your name. The person here. So we've had 1 submission to the leaderboard so far. Who made 11 entries? The last one was 4 days ago. He might be done or he might not be done. It's up to him. So his score is considerably. So basically, if you make a submission and your score is 135.8, that's not, the lower score is better. That's not a good score. That means you've submitted the sample. Go ahead and submit the sample just to be sure. If you gave me nothing but the sample, I would definitely give you a grade. If you give me nothing at all, you'll get a 0. So don't do that. That would be very detrimental to your grade. I don't think it would be survivable. And then so if you get even worse than that, then I really will wonder about you, because somehow your model has managed to do worse than an average of the scores of the training set. And that's always your baseline model. Just take the average. So anyway, 135 is the baseline. You'll want to write that down. So long as you're better than 135, you are in.
What's an optimal score?
0.
0.
That would be a root mean square of 0. It's not possible because there's noise in the data set. So noise is simply things that you can't predict. A good example of that would be we use health attributes and medical records and prescription histories to predict how long people will live for life insurance. What if the athletic runner takes a step out of his house and is struck by lightning or hit by a bus? All his health scores are going to look extremely good, but he died prematurely just due to a random act of nature. So there is noise in this data set, so it should be impossible. I'm thinking the score of 22 is pretty good. I mean, you might be able to improve upon that, but that's probably the best. That's a good one. Any other questions?